Okay, so here's a problem where again we're asked to find the shear force and bending moment as functions in the structure. And you can see that over the first 12 feet I have a continuous load, so I can get a set of equations that are valid there. But then from 12 to 20, I'll get a second set. And then we'll check to see if they're matching at x equal 12 feet. I think what I'll do is try a different procedure than I did last time because it's a cantilever. So in the first case, what I want to do is cut the structure somewhere in the middle, right? And that would be at some distance x from the left-hand side. Now you have to decide, do you want to work the left side or the right side? Left side looks like the way to go. But to get the left side, I'm going to need the reactions. So let's.
Why would the left side be easier than the right side?
We can work the right side. You want to work the right side?
I just wondered, just because there's no reaction forces on the right
well,
side.
let's work the right side then. So I don't need reactions.
20 minus x.
So I'll just draw a free body diagram of the right-hand side. So this will still be an equation that's only good between x equals 0 and 12. Okay? Because when we go outside of 12, then this free body that I'm drawing here is not going to work. So let's do that. So I'll draw the free body diagram of the left-hand side. So I've got a 20 kip force here. I'm going to have some portion of the distributed load, which is 4 kips per foot. Now to help you visualize this, remember that x from the left-hand side is to here. So what would be the remaining length of this bar? This plus this has got to equal 20, so this is going to be 20 minus x. Everybody see that? Now also, in this particular problem, this little cantilever, or this little second load piece is 8 feet, right? So I would need to know this little piece. You can see it gets a little more tricky how to keep up with that. So what would this be? If this piece is 20 minus x, and this is 8, this piece would be 12 minus x. Everybody see that? So x can be anything it wants, and then these values will automatically adjust. You can check it. What happens when x is equal to 0, which means I go all the way to the free end. Then the right-hand side would be 20, 12, and 8. If I go all the way to the other side where it's right at 12, then this cancels out. I have 8, 8, and 8 match. So it seems to be working okay. So now let's deal with, I need to deal with this force, so I now have to deal with the concentrated equivalent force. I'll just call it F. So what is F equal to? What's the area under this curve? Base times height. So that will be 4 times 12 minus x. Okay? And from the cut, what's the distance? I'll call it D. So what would D be? Well, it's half the base, right? So that's going to be 12 minus x over 2. At the cut surface, I have positive shear force and positive bending moment. So I think that's everything on my free body diagram. So let's see what we get. So let's sum moments about the cut. And I advise you just kind of leave things like they are. You don't necessarily have to feel the need to expand your polynomials. You might just want to leave them in the factors. So starting here, I've got the moment, which according to my sign convention is negative. About the cut, F creates positive or negative moment. Negative. And the force would be 4 times x minus 12 times the distance, which is x minus 12 over 2, right? And what else do I have? This 20 creates negative moment. And what's its distance? 20 minus x. So you can solve for the moment. The moment as a function of x is all that stuff. So it looks like it's minus 2 times 12 minus x squared minus 20 times 20 minus x. Now obviously you could expand that if you wanted to and make it simpler, but why? It's an equation, right? Does it work? What's the moment at b? 0. So if I put an x equal 20 here, what do I get? Oh, I don't get 0, do I? Oh, I'm sorry. I messed up. My equation only goes from 0 to 12. I can't put 20 in. But I can put 0 in. If I put 0 in, what do I get? Well, I'll get a value, and if you check, that would probably be equal to the reaction. We didn't solve for the reaction. I can't do anything right now. So I don't get that warm, fuzzy feeling that I can check anything. But I can go ahead and do what? Some forces in the y direction and see what my shear force is. So I've got my shear force acting up, my force acting down, that's minus 4, 12 minus x, and then minus 20. So it looks like the shear is equal to 4 times 12 minus x plus 20. And that would have units of kips. I forgot to put my unit up there. I'll go back. Makes it a little more problematic to do the derivative, but you still can do it. And the derivative of this is that term. And believe it or not, the derivative of this is 20, so it matches. So far, the derivative of my moment is equal to the shear force, so it looks like I'm okay. Unfortunately, I've run out of time, so I'm going to have to stop here. So we'll pick it up here on Thursday. We'll just finish the problem for the free end, and we'll work some more. Okay?